Hello, everyone, and welcome to Opensearch Con. I'm Cameron, a principal engineer working on the Opensearch infrastructure team at Atlassian. So I'll be talking about our experience running hosting Opensearch on Kubernetes. Here at Atlassian, we use Opensearch for a number of different use cases. So we use it for storing high-volume operational data across a number of internal services to optimize our platform. We use it to power Jira Search, allowing customers to search using JQL across their work items. We also use it to power user search across all of Atlassian's products. And lastly, we use it to power Rovo, which enables AI-powered search across all of an organization's Atlassian and third-party applications. So just a bit of background on our scale. So we have over 300,000 customers, 2 million monthly AI active users, and 13 regions worldwide and growing. So in Opensearch, this translates to like a large number of clusters. We have over 300 individual clusters, 2,000 nodes, and about 20 billion documents in some of the larger clusters. So this obviously presents a lot of challenges. As most of our use cases are directly serving customer traffic, we can't tolerate any downtime for maintenance. The large number of clusters also means we need like automatic provision and management of clusters, and we don't want to be manually orchestrating individual upgrades. So some of the use cases require on-demand creation of the clusters when a customer creates new sites, and that means we need automatic and reliable provisioning. And we also need to be able to support multiple cloud providers. So what are the advantages of Kubernetes-based solution? So Kubernetes extracts away a lot of the cloud-specific details, and we're able to build a solution across multiple cloud providers. It also allows us to configure clusters in a way that's more suited to our use case, for example, like read-write separation. And it allows a quick response and quick workarounds for issues that may affect cluster performance or availability. And we also use, we can also use existing battle-tested components for observability and monitoring. So at Atlassian, the Kubernetes team will manage the metrics, logs, and other observability and security concerns, freeing us up to focus on the OpenSearch-specific aspects. With that said, this is the solution we settled on. So we have a control plane service that maps requests from our internal microservice control plane, and that allows us to provision custom resources in Kubernetes, which are then picked up by the open source Kubernetes operator to provision the Opensearch cluster. And we are using Splunk, but maybe someday that'll be Opensearch. And so for those unfamiliar with and operating in Kubernetes, it is an additional component that you can add to your cluster. It will add custom resources, and it abstracts away the details of provisioning like high-level resources like an Opensearch cluster. So the operator just watches the custom resource API in Kubernetes and automatically provisions any sub-resources. So this pattern basically allows us to easily build reusable components, and it's basically allowed us to build upon the existing community work that's been done to build an operator. So the first challenge we had with the operator was that it was very difficult to tell when a cluster had been upgraded. Whether the cluster had updated successfully. And so, for example, if you deployed to one environment, you would want to know that's successful before moving on. And the only real way to do this at the time was to check all the sub-resources had been updated correctly. But this is very fragile and would introduce a lot of complexity. So a common pattern in Kubernetes is to use conditions in the resource status. The condition exposes whether the resource has been updated, and this allows us to reliably know when the update is succeeded. So that the deployment can proceed to the next environment. And so we can see here, along the bottom here, an example of the status reporting. And so we can see here that like the top cluster is doing a blue-green migration to a new set of nodes. The next one is doing has been failed because the user's incorrectly configured the volume mounts. And then we've got the third one doing a rolling restart. And then finally, the last one is successful. So it also introduces a massive amount of benefits. It's much easier to identify why a cluster's stuck or not provisioning, rather than like separately searching logs. And in our case, other teams use our platform to provision clusters, and so this basically allows us to easily have them figure out the problem on their own rather than us being contacted. And secondly, it makes like testing a lot easier because you don't need to wait until the a timeout expires. You can just see the error straight away. So the other challenge we had was around upgrades. So as mentioned before, the operator handles updates to cluster configuration. This might be, for example, increasing the capacity of nodes or moving to a new version. And there's two ways to do this within the operator. So one is by doing a rolling restart. And that's just updating the node pool directly. And this triggers a rolling update where each node's individually restarted. And so this can be done by excluding nodes and migrating the shards off those nodes, or by just restarting the node. And this is in the operator. This is controlled by the drain node flags. So the former is obviously very faster, but the cluster will go yellow, and also for the period the node is down. And so this wasn't very desirable for us. So if you're draining shards, it can take a long time to individually update the cluster. But obviously, if you're not draining shards, then you'll have that yellow cluster. And so, for whatever reason, if there's a bad configuration or a new node cannot be created, then you'd have a reduced capacity until that node could be fixed. So the other way to handle it was, is a blue-green deployment. So you create a new node pool and then remove the old node pool. And then this is, obviously much faster because you can do that migration in parallel and significantly improved. And the other thing was that, but this is not possible in the existing operator without manually sort of going in there and creating the new node pool. And so if we want to do that automatically, we need some sort of component to go do that automatically for us. And so we figured it's best performed in the operator itself. And so by building it into the operator, other users of the operator would benefit. So how does this work? So the operator just maintains a list of attributes that should trigger the blue-green migration, for example, version, resource sizing, or node selector. And then we initiate an update to the custom resource, and then the operator automatically detects there as change, and then compares the new attributes against tree list. If those are changed, then instead of updating the existing node pool, it creates a new node pool, and then we wait until the node pool has been created to reach full capacity. After that successfully provisions, we then exclude the source nodes, and the data is migrated to the new nodes. And then finally, old managed nodes can be removed from the voting exclusion, and then the original stack can be removed. So this can all happen with inside the operator. So any provisioning layer on top of this doesn't need to handle this. It just handles updating the version from a new version to a new version. And then if for whatever reason the new nodes are not successfully created, then you can just do a rollback to the existing nodes. So the other challenge that we had was around what we call node recycling. So in Kubernetes, Kubernetes likes to terminate nodes. And so occasionally we need to roll out updates to the configuration of the Kubernetes host itself. And this requires migrating all of the Opensearch nodes to new hosts. This is usually okay if just one host goes down, but if you've got multiple, then obviously that's going to be an issue. And so the way this is usually solved is with what's called like a pod disruption budget. And you can set the maximum number of pods that can be unavailable. This does help. However, the issue is that when a new node comes up, as you might know, that hasn't necessarily resynchronized all the data. It's just that that node can now respond, and so you need to wait until that data has been resynchronized. And so we found the best solution is just to have a startup probe, which will wait for the cluster to become green. However, we have found some upgrade paths where you're creating a new plugin, which that might create an index implicitly, and that will cause an issue. But for most cases, it's been fine. And then we're also working on a solution to basically push this to the blue-green deployment path, and that would result in no yellow status. So another area that we've made some improvements in, we've added automatic renewal of leaf certificates. But it sounds like someone's actually independently added this into the public version as well, which is, and then we also want to add automatic rotation of the CA certificate as well. And so we also needed additional CA certificates to support cluster replication. And then we've also migrated the operator to using EC2SA certificates, which improved the pushing speed, and then also worked around some limits on the number of nodes using per node configuration, per node certificates. So another challenge we had was around availability zones. So when you're running a cloud in a public cloud provider or just on-prem in general, you would generally need to split your workload across multiple availability zones. So for running Opensearch, there's two concerns you've got to worry about. The first is that the Opensearch nodes are equally distributed across availability zones. So in Kubernetes, it's usually handled by a topology spread constraint. However, the one limitation is that sometimes when an availability zone is down, because of the, if you've got min domains or you also have a partially working node in that AZ, you might have an issue where it will actually not spin up new nodes in the existing AZs. So we opted to create the volume claims directly, and that meant we could just allocate individual nodes to individual AZs. And it also unlocked us to be able to provision multiple nodes in parallel. So the second challenge that we had with this was basically that you obviously need to make Opensearch aware of the individual availability zone. And this can be done through Opensearch in the node attributes. And for this in Kubernetes, we set up an init container that would pull that down, but there is a new feature in the later version to set this to the downward API. We've also sort of adopted a cell-based architecture approach where we are sharding our Opensearch clusters across multiple different Kubernetes clusters, and this reduces the blast radius for like the Kubernetes level changes. And this reduced size means we don't need to push the limits of Kubernetes scaling. So further improvements. So in Kubernetes, it's typically a pattern that you run multiple pods on the same set of nodes or same node. However, due to like the large size of a typical Opensearch cluster, Opensearch node, and because we want to avoid any effects between different clusters, we opted to just basically use a dedicated host for each Opensearch node in our production clusters. And this allows us to basically maximize the resource of any individual instance and get consistent performance. And that's especially important when you're doing benchmarks. We're also using Carpenter. So Carpenter is a node scaling tool that basically allows you to provision Kubernetes hosts based on what pods need scheduling. And this means there's no buffer capacity that you would need to have otherwise. And it also gives you flexibility to use many different underlying instances types for different use cases. And then we also have the ability to sort of dry run the operator changes. So this is an additional mode that we've added, which allows you to run the operator against any production configuration and then see if there's any possible changes to that. And that obviously reduces risks when you're doing those changes. And because it can detect any unintentional changes by the code in the testing phase. So onto the future. So we want to contribute back a lot of these operator changes. And I'm currently writing an RFC for one of the condition changes. And we're also interested in adopting a lot of existing features that the community has built. So for example, like the segment replication, we've done some testing with that, and we can see some early promising results which show a large decrease in CPU and performance, and improvements in performance. And then obviously the pool-based ingestion in 3.0, which I think was mentioned earlier, basically would enable that blue-green approach to work on a full cluster by cluster with fully independent clusters. And that means that even if you do like a version upgrade, you can still roll back to the old version. And then for this, we're currently using sort of a bespoke dual write approach in the applications, but having a more standard approach would eliminate the errors. So thank you for listening to my talk. If you have any follow-up questions, I'm on the Opensearch Slack channel, and but yeah, thanks.